Good morning. Today we'll be discussing about non-linear pipelined processes, which is in continuation with our previous lecture on linear pipeline processor. So when we discussed about the linear pipeline processors, we had said that the stages are arranged in a linear fashion so that the output of the previous stage becomes the input of the next stage, and also the first stage will ex, uh, accept the external input and the final output emerges at the last stage of the pipeline. So when you're talking about a non-linear pipeline processor, these kind of processors or these kind of pipelines, to be intact, they will have the final results emerging from more than one stages of the pipeline, which means it need not be necessarily from the last stage of the pipeline. An output can emerge from any of the intermediate stages based on the computation that is being required. So if a pipeline helps to emerge the final result from any of the stages, such kind of a pipeline is called a non-linear pipeline. So the advantage of having such a pipeline is that you can have multiple functionalities happening inside the same infrastructure or the same pipeline. So you can use the same pipeline to cater for different types of need, unlike in the case of a linear pipeline processor. Whereas in the case of a linear pipeline processor, since they are linearly arranged, you can use them to complete only one kind of execution or one kind of computation, or they are designed for only some kind of task. But when you talk about a non-linear pipeline, since you can have multiple output stages or multiple final output stages, you can have multiple functionalities happening inside the same pipeline. So that is the advantage of non-linear pipeline. Since this is the property of a nonlinear pipeline, it is said to be a dynamic pipeline, which means you can reconfigure it to perform various functions at different times. Whereas a linear pipeline is said to be a static pipeline. So the dynamic pipeline, in the case of a dynamic pipeline, unlike the linear pipeline, you can have both the feedback and feed forward mechanisms. So in the case of a linear pipeline, it is having a straight feed mechanism, which means, as I said before, the output of the previous stage becomes the input of the next stage. And that has to be the same across all the stages of the pipeline. But when you talk about a dynamic pipeline or a nonlinear pipeline, you can even skip the stages in between. That is called feed forward, or you can go back to a previous stage during the execution, and that is called a feedback pipeline. So these two of these mechanisms are actually possible in the case of a nonlinear pipeline, and hence it is known as a dynamic pipeline or dynamically reconfigurable pipeline. So I'll give you an example for a non-linear pipeline processor. So here you can see this is a three-stage non-linear pipeline. Okay. So when you talk about the three-stage pipeline, this particular arrow that you can see from S1 to S2 and from S2 to S3, that corresponds to the linear pipeline which we have discussed before. But when you talk about this one, which means this particular pipeline can actually be used to serve two different functions. The first function being the normal function, which is having an output y, and the other one being another function which is having an output called x. So when you want to do the function of x, you can configure the pipeline accordingly. When you want to do the function y, you can configure the pipeline accordingly. So here you can see there is a straight connection from the stage S1 to S3. That is an example for feed forward connection. Similarly, there is a connection that goes back from S3 to S2. That is called a feedback connection. A connection from S3 to S1 is there, and that is again an example of feedback connection. So these all are possibilities of a nonlinear pipeline. So the reservation and latency analysis here, when we are talking about the reservation and latency analysis, the partitioning that is happening in a dynamic pipeline will require an extra effort due to the interconnections like feed forward connection, feed backward connection. All those extra connections will actually increase the efforts to program or to reconfigure the pipeline. Okay, so this is the reservation table, a sample reservation table in the case of a nonlinear pipeline. This is for the process called X, and this is for the process called Y. So here you can see, even though it is a three-stage pipeline, the output X is going to emerge at the 8th cycle only. So you will have to maintain the data inside this pipeline for 8 clock cycles, and for that you may have to use um, the feed forward mechanism or the feed backward mechanism or a combination of both. Okay, similarly in the case of the output called Y, even though it is a three-stage pipeline, it is not going to give the output at the 3rd cycle. It is going to give the output only at the 6th cycle, which also involves a feed forward or a feed backward mechanism, so that only in the 6th clock cycle your actual output will be taken out from the pipeline. Okay, so this is also an example of non-linear pipeline processor, the reservation table for a non-linear pipeline processor. So we'll have a problematic exercise of all these concepts, how to write the reservation table, how to know the stages of a pipeline, all that we'll be discussing as a separate lecture during the course of this module. But as of now, I'm limiting it only to the theoretical portion of it. So the reservation and latency analysis, as I said, we have the feed forward connections and feed backward connections from S1 to S3, from S3 to S1, from S3 to S2, and so on. The feed forward and feedback connections will help to make the scheduling of successive events into the pipeline more easier, and the output of the pipeline, since we have the feed forward and feed backward connection, you don't have to keep the last stage as your mandatory stage for output. You can have an output emerging from any stage of the pipeline. Then you can follow different data flow patterns, and you can create or you can design the same pipeline to cater for multiple functionalities. Then about the reservation table, as I said, in the case of a linear pipeline, you can see that the reservation table will be following a sequential order or a linear fashion. But in the case of a dynamic pipeline, it follows a non-linear fashion. So the multiple reservation tables can be generated. Even the same pipeline, the same configuration of a pipeline can have multiple reservation tables based on the functionality. So multiple reservation tables can be generated for evaluating various functions, and each of the reservation table will be displaying the time space flow of the data through the pipeline for one evaluation, for one function evaluation. So even if the pipeline is capable of supporting multiple functions, we are limiting to one function at a time and one reservation table per function. So each of the reservation table will be displaying the time and space flow of data through the pipeline for one function evaluation. So different functions are, if different functions are there, they will be having different paths through the pipeline. Then about the latency analysis, you can simply say that the evaluation time of a function is equal to the number of columns in the reservation table. So just like I said before, the function X was giving an output only in the 8th clock cycle. So definitely your reservation table will have 8 columns. Okay. So when you talk about the evaluation time, you have to just look into the reservation table, identify the number of columns, and then you can say what is the evaluation time for the function. The pipeline initiation table corresponds to each function evaluation, and in the case of a linear pipeline, all initiations will have the same reservation table, whereas in the case of a dynamic pipeline, there will be different initiations, and it will follow a mix of reservation table. So each row of a table will be referring to the time instance where a particular stage is being used. As you have seen in the reservation table, all the rows corresponds to various stages and all the columns corresponds to clock period. So whenever you see a mark in the row that corresponds to this thing, that at that particular clock period the corresponding stage is under use. That is what meant by a mark in a particular row and column of a reservation table. So if you have multiple check marks in the same row, that means that the same stage has been used again and again throughout the evaluation of the function. And multiple check marks in the same column means that multiple stages are being used in the same time. Okay, which means parallelly multiple stages of the pipeline are being used in the same time, and that is multiple check marks in the same column. Multiple check marks in the same row means repeated use of the same stage. So all these are the points to be noted about the reservation table of a nonlinear pipeline. Now, as I said, the latency analysis, when you talk about the initiation latency, it is the number of clock cycles between two initiations of a pipeline. So, if it is k, that means k clock cycles will be there between the two initiations. So, if you have two initiations, like if stage S1 has been used in cycle number 1 and later in cycle number 5, then the cycle number 1 corresponds to the first initiation of S1 and cycle number 5 corresponds to the second initiation of S1, the stage S1. And the difference, the time difference or the clock cycle difference between these two initiations is called the initiation latency. So when you talk about S1, it is 5 minus 1, 4 is the initiation latency. Collision. So if two or more initiations try to use the same pipeline stage at the same time. So you have multiple initiations and all those initiations are trying to use the same stage at the same time. That is called collision. So if there is a collision, that is an indicator that there is a resource conflict, which means the same stage, the same functionality is supposed to be reused at the same time, is supposed to be accessed at the same time by multiple initiations. So that results in a resource conflict. So what happens? You cannot support a resource conflict. You cannot support a conflict to happen. And in that case, you have to resolve. So what you do? You will identify which all are the latencies that should not be allowed for initiation. Such kind of latencies are called forbidden latencies. So we have a big problem to go, a big design problem to go based on all these. So when we are actually making the solution for such problems, you will understand it better. Now, as of now, I'm just giving theory part. So please do understand what do you mean by this forbidden latency and all that. After that, you will be practically doing it by your own and you will have a better understanding. So this is a sample of a collision. So here you can see here a function. So this is a reservation table. So here you can see an initiation table actually. So here you can see x1 starts with the stage s1 at cycle number 1. Later in cycle number 3, x2 has started with the same stage. Okay, this was actually under use by x1 and at later stage x2 has also requested for execution. But you can see when it comes to the fourth clock cycle, both x1 and x2 are requesting. X1 is one initiation or one function, x2 is another function. Then they are requesting for the same clock cycle or the same stage, and that is a perfect example of collision. So this is a collision with scheduling latency of 2. Similarly, there is a collision between x2 and x3, x1 and x2 again, x1, x2, x3. All these have a scheduling latency of 2, and this is an example of collision. So what you have to do, you have to resolve the collision and you have to make the better performance out of the nonlinear pipeline. Now this is with the scheduling latency 2 and this is with the scheduling latency 5. Here you can see the first initiation of S1 happens at the clock cycle number 1 and the second initiation happens at 6. So this is in the case of X1. But in the same clock cycle of 6, X2 is also requesting for the same stage, and that is a perfect example of collision. So this is having a latency of 5. Okay. So this is just to make you have a better understanding on what is this latency, that what is collision and all that. Now moving further, the reservation and latency analysis. While we are identifying the forbidden latency, you have to first calculate the distance between the successive checkpoints of a row. Then based on that, you will derive the forbidden latency. The latency sequence, it is the sequence of permissible non-forbidden latencies between successive task initiations. So when you identify, just like you identify the forbidden latency, you also identify the permissible latency, where you can support initiations happening within a a particular stage. So that is called permissible latency. So when you talk about the latency sequence, it is nothing but the sequence of permissible latencies that can be there between successive task initiations. Moving on, what we talk about latency cycle is that it is a latency sequence which is found to repeat itself indefinitely. So if a particular latency sequence is found to repeat itself for indefinite times, such kind of a latency sequence is called latency cycle. Now talking about the average latency is nothing but taking the sum of all the latency permissible sequence of permissible latencies and then finding its average. It will be the average latency. Okay, constant cycle or constant latency is that the cycle or the latency cycle will be having only one value. So if that is the case, then such kind of a latency is called a constant latency cycle. Okay, so these are some of the terminologies associated with reservation and latency analysis of a nonlinear pipeline processor. So this is some example. So here you can see this is a latency cycle, because you can see it has got a peculiar order like 1 8 1 8 1 8. This is happening uh, for indefinite times. Okay, so this is a latency cycle, and when you take the average, it is having an average latency of 4.5. Similarly, this is another cycle, but this cycle is actually a constant cycle because each of the latency is 3. So obviously the average latency will also be 3. Moving on, this is another example. Here the sequence is 666. It is again a constant cycle, and it is also having an average latency of 6. This latency is nothing but the time difference between successive initiations of a particular function. Then talking about the nonlinear pipeline processor, again we have to talk the mission while you are designing a nonlinear pipeline is that you should create a collision free scheduling. Okay, so you should schedule the events in the pipeline without any collisions. So that should happen with shortest average latency. So this is your mission. Your average latency should be minimum, and also there should not be any collision. So such kind of a design is said to be a good design. Okay, so it's scheduling the event so as to obtain the shortest average latency between the initiations without causing collision. So about the collision vector, I'm just repeating the same. I'm saying that when you actually do the program, when you actually do the problem, there you will understand all these: what is collision vector, what is permissible latency, what is forbidden latency. All that you can just practice with your practice by yourself itself. So please don't worry about all that. We'll be doing that, but this is for the theory purpose. Okay, so collision vector is nothing but the vector which corresponds to the permissible latency and forbidden latency, and the permissible latencies will be denoted, and the forbidden latencies will also be denoted in the collision vector. So if the number of columns is equal to n, then you have to understand that the maximum forbidden latency is n minus 1. Similarly, permissible latency p should be as small as 1 less than or equal to p less than or equal to m minus 1, where m minus 1 is the maximum possible forbidden latency. Okay, collision vector is going to, as I said before, it will indicate both permissible and forbidden latencies, and it will be normally a binary vector. It is a binary vector, which means it will have either of the two values, 0 or 1. So a collision vector of m bits will be having this kind of a representation, which is cm, that stands for the maximum bit, and 2c1, that is the minimum bit, or the minimum what do you say, the least significant bit. So if you find a 1, then that corresponds to a collision, and if it is 0, then it is permissible. So that is how you write the collision vector. Wherever you have a forbidden latency, you have to represent it with the 1, and all the permissible latencies will be represented using 0. So if Cm is equal to 1, then that is the maximum forbidden latency. Now talking about the nonlinear pipeline again, we have to know what is a state diagram, and the state diagram is nothing but a diagram which corresponds to the permissible state transitions among the successive initiations. So you have to draw the permissible state of the pipeline, permissible state of the collision vector, or you will be using the collision vector to derive all the successive stages. So that is the state diagram, and the collision vector will be the initial state of the pipeline, which is at the time 1, and you have to make use of the state transition on a particular order, which is that next state at time t plus p will be derived using an m bit right shift register. So you have the initial collision vector, you have to apply a right shift. Remember, it is a shift, not a rotation. So you shift to the right, and if it is, and based on that shift, you will decide on what is the next stage to come. So each 1 bit shift of the collision vector corresponds to an increase in latency by 1, and if the shift makes a 0 to emerge from the right side, then it is a permissible latency. If it is a 1, then that is a forbidden latency. Okay, so you can derive the next state by using the bitwise OR operation on the collision vector with the contents of the register. So all these, how to derive the state diagram, how to draw the state diagram, how to derive the next state, all these will be handled in the problem. So by then you will have a better understanding. Okay, so I'll show you a sample here. So this is actually the state transition. Okay, so you have a collision vector, you are applying the right shift, and this is the state diagram. Okay, so this is an n bit right shift register, and n is the maximum forbidden latency. So you have to apply the right shift. So whenever you are applying the right shift, you are supplying 0 from the left end. So that you have to remember. Whenever there is a right shift, you have to supply 0 from the right end. And if it is a 0 that is being emerging out of the register, that corresponds to a safe state. 1 corresponds to a collision. So if it is a safe state, you can make use of the bitwise OR operation to derive what is the next state. If it is a 1, then you have to simply discard. So this is a sample state diagram. I will explain this using the problem itself. And this is for the function x that we have discussed in the first slide of this lecture, and this is the state diagram corresponding to the function y of again the first slide. Now moving to the last part of this module, the last slide, we have to talk about the state diagram and the greedy cycles. So the state diagram, as I said, it is going to cover all permissible state transitions that can avoid collision, and greedy cycles are those cycles which will have minimum average latency, which we call MAL, minimum average latency. So all latency is equal to or greater than M. M stands for the maximum forbidden latency, are permissible. Then the collisions can be avoided if the events are scheduled far apart. So if you can guarantee that the events are scheduled as far as possible, then you can also guarantee that the rate of collisions will be less. Greedy cycle. To know about greedy cycle, first you have to know what is a symbol cycle. So a symbol cycle is a cycle where each state appears only once, which means you will not be revisiting the state anywhere during the course again. Okay, so once if a state is visited, it will not be revisited. There is an exception for the starting state because this is a cycle. So the starting state can appear twice, and all the other stages should appear only once. If that is the case, such kind of a cycle is called simple cycle, and a greedy cycle is again a simple cycle which is having minimum latency uh, compared to the other simple cycles of the same state diagram. Okay, so greedy cycle is a simple cycle whose edges are all made with minimum latency, and as I have said before, they are called greedy because they are trying to reduce the average latency, and the at least one of the greedy cycle will be definitely having the minimum average latency possible. So our mission is to identify that cycle and schedule the events according to that particular cycle. So that is the whole mission of scheduling a event in a non-linear pipeline. That is the problem all about. So that's all about this module. So if you have any doubts, you can contact me. So that ends the fourth module, theory portion. We have some problems remaining, and that will be taken in the upcoming lectures. So that's all. Thank you.